So you see now the lecture notes, right? I will probably enlarge them. Okay. So we should finish the first lecture still. So we have derived the conservation of potential vorticity. And if you do the exercises, you will see that it can be very useful. This law is very useful to understand flow over mountains. It's really a very, very powerful tool. If you continue to do climate or atmospheric dynamics, this law will accompany you everywhere you go. I think it's a very, very powerful and important law. Now, there's a very more general version of this law. Sometimes, the more approximate versions, they are sometimes useful, more useful maybe to do applications because it's easier to insert numbers. Sometimes the more general law is kind of a little bit more difficult to interpret, but it's good to know the background for this conservation law in principle. So the conservation law for potential vorticity is a very, very generic conservation law that has been discovered many decades ago. So if you write down, and now I want to try this tool. If you write down the momentum equation, in this case, the three-dimensional momentum equation. So that's equation 23 here. I'm now learning how to annotate. PDFs. So we see the three-dimensional momentum equation. So this is similar to the two-dimensional one for the two horizontal components that we have derived in the last lecture. But we can be a little bit more generous. So first of all, this contains the vertical component also, which we, most of the time in this lecture, we will make the assumption that the hydrostatic equation is very much fulfilled in the vertical direction. And even in today's lecture, we will make use of this property. But we try to be as much as possible general here, so we don't need to make this assumption to derive the potential vorticity conservation as a general law. It's even better to make no assumption here right now. So we can write down the essentially Newton's law for the motion of atmospheric parcels. And of course, you have named this already. There's the pressure gradient force. There's the Coriolis force. In this three-dimensional form, it looks a little bit different. There's not F, but there is this constant rotational vector of the Earth, which is just giving us this rotation vector of the Earth. And we have to consider that this is a constant vector. However, if F is variable because you take one component of this vector that is varying along the surface of the Earth. But if you take the full vector, it's a constant vector. And this is used in this lecture. And then there is the acceleration due to gravity, which we didn't see in the last lecture because it comes into play because we have the three-component momentum equation here. And we can have frictional forces here written in a way that is the convergence of the friction tensor. But you could also just write it as a vector that contains the frictional terms. I don't think we make any use of this property here. Now, how to derive from this the vorticity equation? Same thing, we apply the rotation to this equation. We apply Nabla times the momentum equation, and we get an equation for the vorticity, which is written down here. And this will be an exercise, of course. This is quite a complicated exercise involving vector algebra, but I encourage you to do it. If you are sometimes uncertain about validity of vector identities, you can just write them down then in Cartesian coordinates, and you can verify that they are valid. So we can derive an equation for the absolute vorticity. Now it's a three-dimensional vector, because before we have derived the equation for the vertical component of the absolute vorticity. Now we have a three-dimensional vector, which has vertical and horizontal components. And there are a few terms. Some of these terms we remember. This is the sinusoidal term, remember, that we had also for the vertical component. Only that there we only took the vertical component. Here we have to use the three-dimensional. We get a divergence term. This is the divergence term that we have derived also in the last lecture. And we get this term here, the vorticity times gradient of the velocity. So this is another term that occurs here. And an effect of the frictional terms. As I said, we want to be as generic as possible in this during this derivation. So the absolute vorticity is then defined as 2 times rotation vector of the Earth plus the vector, in this case, for relative vorticity. So relative vorticity is also a vector here. It's not just one component. And omega is constant, and that is used during this derivation. Now, using the continuity equation, you can eliminate this term here, because, let me try if I can, d rho by d. This is not so easy. No, I don't think this is possible. Anyway, you know that d rho by dt is equal to minus rho times the divergence. So you can eliminate the divergence in this term here by using the continuity equation. So you insert here the continuity equation, and you can derive an equation for the vorticity divided by the density. So it turns out you can combine these two terms essentially and write down this equation here. So this equation looks like the previous one, divided by the density, and then we get the total derivative for this quantity here. So we have made already one step forward. We have eliminated one term on the right-hand side and brought it into the total derivative on the left-hand side. This will be the exercise, because if we manage to remove as many as possible terms from the right-hand side, the source terms, then we may able to derive a conservation law on the left-hand side. Because if we have no term on the right-hand side, that means the quantity for which we have the total derivative, that total derivative is 0, and therefore it's a conserved quantity following the motion of a parcel. And so they now use a trick. Imagine we have a scalar quantity, in this case called lambda, which is just a function of density and pressure. So for one component dry, for example, dry air system, this would be any thermodynamic quantity. So temperature, potential temperature, whatever you take would fulfill such a property. And for this quantity lambda, which we will specify later on, and it turns out this will be specified for our case as the potential temperature, but it could also be entropy or something else for the ocean. We can write down a generic conservation law, or what we call balance equation. So we say the rate of change of this quantity is equal to a source term. This will be a generic form for, and this source term can contain everything. Also diffusion terms and so on. Everything is packed into this source term, can be an arbitrary source. But if the quantity is conserved following a motion, then the source term would be 0, the sigma lambda. Now you can do again, I remind you that it's always good to verify things in Cartesian coordinates. So one can verify very quickly in Cartesian coordinates the validity of this identity 27. So if you want to validate this, you have to do this in Cartesian coordinates. It's the easiest way to do. So we can write down the vorticity scalar product, rate of change of the gradient of this quantity lambda. That would be equal to the vorticity times scalar product, the gradient of the source term, minus vorticity times gradient of the velocity scalar product with a gradient of this quantity. So it looks quite complicated, but the reason why we do this can be seen immediately, because now if we multiply this equation here, the vorticity equation slightly modified, with the gradient of lambda, scalar with the gradient of lambda. So what we get now is a scalar, because we have a vector and another vector, and they are multiplied in a scalar form. So then you can show, this is just multiplying the whole equation by gradient of lambda. But if you compare this equation now with this equation, we can see that we can try to combine these two terms. So if we add these two equations now, then we are also lucky that, for example, this equation, this term here, after dividing by the density again, this term here will probably drop out if we add these two terms. So that's the idea. We divide this equation here by rho and add these two terms. And then we find the following. The total derivative of a complicated quantity, which is the gradient of this scalar quantity lambda, scalar product with the vorticity, with the absolute vorticity divided by the density. And that has the following source terms. The first one is the gradient of lambda times the cross product of gradient density and gradient pressure. The second term is related to the gradient of the source term of our quantity lambda. And the third term are the frictional forces, related to the frictional forces. Now we can immediately identify several conditions under which this quantity on the left-hand side is conserved. One is we have a barotropic fluid. That means that the lines of constant pressure and lines of constant density do not intersect. But that is a very special condition, which we had before, but not necessary. Because it's enough already to make this sinusoidal term vanish. It's enough already that the quantity lambda is a function of, the quantity lambda should be conserved itself. So here comes into play that we may consider, for example, the entropy, because the entropy for adiabatic reversible motion, if you have learned in your thermodynamic course, is a conserved quantity. And so is, since entropy and potential temperature are it's a nonlinear transformation, so is potential temperature. So potential temperature for adiabatic reversible motion is conserved following the motion. So in that case, this second term vanishes. The first term vanishes also already if we just consider, for example, entropy, because entropy is just a function of pressure and density for a simple, let's say, one component system, which is the easiest to use here. Because then the gradient of lambda can be expressed as the gradient proportional to one component which is proportional to the gradient of pressure, and one component which is the gradient of density. And that scalar product will identically vanish. So this, you can make sure yourself of this. This will identically vanish once we have picked a quantity that is just a function of pressure and density. because I try again. The gradient of lambda will be d lambda by dp. Wow, this tool tries to interpret something. Anyway, I want to write the gradient p plus d lambda by d rho, gradient rho. And these two terms, they make this cross product vanish. Both two terms multiplied with this cross product, they vanish. So if we have frictionless flow, adiabatic reversible anyway includes already frictionless. Adiabatic reversible flow plus this quantity, which is, let's say, entropy or potential temperature, then all the terms on the right-hand side vanish, and we have a conservation law for this quantity. So in that case, this quantity, which we may call Q, is called potential vorticity. It's one of the few conserved quantities for geophysical, is a very general conserved quantity for geophysical fluid, or for fluid dynamics in general. There's nothing related to geophysical here. It's a very general conservation law for adiabatic reversible motion, frictionless flow. And it's very, very important because conserved quantities are very useful. It turns out to be very useful later on also if we think of how the general circulation mixes quantities, because we can only really try to understand a mixing property if we have a principle, a conserved quantity that is mixed. If while a quantity is tried to be exchanged with latitude bands, but the quantity then loses already its property, it's not possible really to think of a mixing of this quantity. So therefore, this potential vorticity assumes a very, very important role in fluid dynamics, and also in particular in geophysical fluid dynamics and in climate and atmospheric dynamics. As important as also important is the potential temperature or entropy themselves, because they also obey this approximate conservation law. At least we can consider it conserved if we assume adiabatic reversible motion. Now, so it turns out for our atmospheric purposes, we can pick either the entropy or the potential temperature. And you know how they are related, no? Entropy is equal to, anyway, Cp ln, the other way around, S. So this would be theta, sorry. You can imagine. So theta is equal to Cp ln entropy. So there's a nonlinear transformation between the two, because entropy is a complex function, but potential temperature has the dimension of temperature, as you know. But in principle, if one quantity is conserved, also the other quantity is conserved, because they are just, it's just a nonlinear function. Now, once we pick, let's say we pick the potential temperature, which indeed is just a function. If you look it up in your lecture notes from atmospheric thermodynamics, it's just a function for the atmosphere, let's say. It's just a function of pressure and density. Then there's one way to simplify this equation a little bit further, knowing that the vorticity is dominated by the vertical component. This is what we, the vertical component of the vorticity is proportional to the curl of the horizontal velocities, whereas all other vorticity components contain the vertical velocity derivatives, which is small. So that means it's the vertical component here that is dominant. If we make use of this, we can immediately show that then the scalar product becomes approximately absolute vorticity, so relative vorticity plus planetary vorticity divided by density times d rho, d theta by dz. So we get the stability coming up here, the density remains, and the absolute vorticity. So we have a triple product here, which makes this a little bit complicated. But we will see that once we have transformed, that was what we will do this in the next section. We transform many quantities into the pressure coordinate system. And then this triple product becomes a double product, just a product of two quantities. So it's a little bit simpler. And just for consistency, it's also possible then from this generic conservation law to derive the barotropic vorticity equation 19 by identifying lambda to be just the relative height of a parcel within the system. So Z, that would be the position of the partial minus the bottom topography divided by the total height of the system. This quantity is conserved, and therefore it can be derived that this generic potential vorticity can be used indeed to rederive again our approximate version. And then there are some exercises, okay, that are also related to the derivation of this of the potential vorticity, which I encourage you to do at least over the weekend. Now we want to discuss properties of the quasi-geostrophic motion. But in order to do this, a very useful thing is to transform the basic equations that we have into the pressure coordinate system. Are you aware with this coordinate system? Have you come across this? I think everybody who has used in the past what is called reanalysis data, you kind of observed a mix between model and observations data set that for the last 50 years or 60 years that can be used to do climate analysis. Every one of you, probably not many, but the ones who have used that data, the data is usually stored in the pressure coordinate system. All climate models, I would say virtually all climate models, apart from maybe now, since models are getting more high resolution, there could be a few exceptions. But virtually all climate models are posed in the pressure coordinate system or small modifications of this pressure coordinate system. So there are some modifications of this, some scaled pressure coordinate system. So instead of using the pressure as the vertical coordinate, you can use the pressure divided by the surface pressure, for example. And that also defines a new coordinate system. But so in order to derive this, we first write down again our momentum equation in the simpler form. It's the one that we had before already, but now we use the vector notation for the two horizontal velocities u and v. So this is again our Euler equation. But in the vertical, we assume something different. In the vertical, we assume that there is this hydrostatic equilibrium. And how good this is. So how does the vertical momentum equation look like? The vertical momentum equation would contain an additional term proportional to the acceleration of the vertical velocity, right? dw by d dt, anyway. So that's a vertical acceleration of the parcel. Let's just for our synoptic scales that we have already introduced, let's just estimate what's the accuracy of this hydrostatic equation for the scales that we are interested in. Because if we estimate rho times g, so rho would be 1, right? That's what we said, about around 1. G is around 10. So the order of magnitude of this first term here is 10. What's the order? Okay, then by definition also you can work out that the pressure change with height, if it has to balance this, it has to be of the same order. But you can easily work this out. How quickly the pressure changes with height will exactly balance this here. But what about the acceleration term, this vertical acceleration term, dw by dt? We can insert our synoptic scale vertical velocity. We are talking about large scale vertical velocities, not convective scale. Convective scale, this approximation may break down. So synoptic scale vertical velocities, we have estimated that is 10 to the minus 2 meter per second. (10 to the minus 2), and the d by dt time scale was 10 to the 5, 1 day about. So we have 10 to the minus 2 divided by 10 to the 5. That's 10 to the minus 7. So we compare 10 to the minus 7 order of magnitude with something like this 10. So that is 8 orders of magnitude difference. So this tells us that we are not talking about some rough approximation here of the vertical momentum equation. But this is a highly valid for the flow scales that we are interested in. This is a highly valid approximation, the hydrostatic equation. 8 orders of magnitude. So this is huge. You could, measurement errors could immediately, if you were to prove that this law is not valid, you would be very much in difficulties, because in order to measure terms that could violate these equations at the large scale, you will struggle to, because of measurement accuracies. The story is different if we go to smaller scales. So it has turned out, if you want to go to scales that are maybe smaller than 10 kilometers, as I said, we are talking about thousands, hundreds and thousands of kilometers of scale. But if you go down to scales that is kilometer scale, then the vertical acceleration term could become more relevant. And it's not such a good approximation anymore to ignore that term in this equation. And you may then use what models that exist that are non-hydrostatic models. Regional scale, high resolution, very high resolution models can be non-hydrostatic, which means that they use the full vertical momentum equation. But as I said, most climate models that have a lower resolutions of, let's say, typically hundreds, 50 to 100 kilometer at least, one grid cell, they are still using this pressure coordinate system. And why is this law important? Because when because in order to perform a transformation from one coordinate system to another, you need a monotonic relationship between your new coordinate and the old coordinate. Monotonic, and that is exactly the case, because dp by dz, the change, is given by something that can only be negative, because the density can never change sign. It's always positive. And G is just for our purposes a constant. So there's a monotonic relationship between pressure and Z. And whenever this is the case, whenever you find a quantity that has with the vertical direction a monotonic relationship, then you can use this new quantity as a vertical coordinate. So there are also the potential temperature, for example, is used as vertical coordinate, because approximately, not everywhere, so that law is a little bit shaky in some occasions, but the theta by dz, we know for a stable atmosphere, is always positive. So if that is the case, we may again use the potential temperature as vertical coordinate. That may have troubles then if you go to the boundary layer and things like this. So you may encounter problems there. But indeed, some theoretical developments, at least, and even some models have been developed using the potential temperature as vertical coordinate system. But most of the vertical coordinate systems used in the literature and in models are somehow based on the pressure coordinate. Either it's pressure or it's something directly proportional to the pressure, or a combination of pressure and something else. Now, how do we derive now the new equations in this new coordinate system? The basic assumption is then that obviously any quantity I look at using the pressure as the new vertical coordinate has to have the same value at any place as the original quantity. So if I look at the temperature using the same place but just a different coordinate, it should have the same value. That is essentially the only equation we need. So with this, then we can derive, for example, what is the rule for a derivative when keeping the pressure constant. So when we apply d by dx to this expression here, we have to keep the pressure constant. But if we derive then, if we apply the same derivative on the right-hand side here, then we have to keep the z constant, but we have to assume that z can be should be dependent on p. So we also have to use the chain rule to say, okay, we also have to use here the d psi by the z, and then dz by the x, keeping p constant. So this is our basic transformation law for any gradient. If we apply this now, if we let this quantity psi be equal to the pressure, and we apply this rule, you can see that the transformation of the pressure gradient force that we need in the equation 33 here can be written as rho times gradient, now keeping pressure constant, of the geopotential height. Because we have made use of the hydrostatic equation by deriving this equation. Now, this makes the horizontal momentum equation simpler, because if we insert this result here now, the horizontal pressure gradient in this equation here, the density drops out. So instead of a nonlinear pressure gradient force, we now have a linear pressure gradient force, or geopotential gradient force in this case, that leads us to the acceleration of our flow. So our equation already has become a little bit simpler. It's still exact in the framework as much as the hydrostatic equation is exact. This equation is now exact. So it's exact, it's not 100% exact, but it's exact to a high degree of magnitude, let's say. The hydrostatic equation can be simply reversed. You just reverse this hydrostatic equation here and you get an equation for the change of the geopotential height with pressure instead of pressure with height. And if you insert the perfect gas law, so our density, we replace our density by P over R, the gas constant of dry air, let's say in this case, times absolute temperature, then this is now our new hydrostatic equation that we can use. So yes, you can see already the gradient of the geopotential plays the role of the gradient of the pressure. It's just a different point of view. Well, we will exercise this. Now, it turns out the total derivative is invariant to this transformation. So you can write down the total derivative according to its definition, d by dt plus d by dx of d of u, which is dx by dt, and so on. But the last term here has to take into account that our quantity is not dependent on z, but it's dependent on p. So it's d by dp by dt. And with that, we can introduce a new vertical velocity, the pressure vertical velocity, called omega. And then our total derivative just looks like this, just like our commonly used total derivative, but in the vertical direction, we have to use omega, vertical pressure velocity, times d by dp. So omega is now this pressure vertical velocity. It's often called, yes, omega in metrology. And the maybe sometimes counterintuitive thing is that it has opposite sign to the real vertical velocity. So you can show this approximately by noting that the main term in this equation here is w dp by dz. So omega is approximately w dp by dz, which is w rho g, but with a minus sign, approximately. So our omega vertical velocity is approximately, if we use this approximation, that this total derivative is mainly governed by w dp by dz, then our omega vertical velocity is proportional to the real vertical velocity, what with a minus sign, and there is a factor of, the typical magnitude will be that the omega velocity is a factor of 10 in terms of magnitudes larger than the real physical vertical velocity w. But this is just something we have to keep in mind, that when we say omega is positive, we mean actually that the flow is going towards increased pressure, which is going downwards. To derive the continuity equation, we could use the full continuity equation and apply the transformation rules for the divergence and for the advection terms and transform it into the form used for the pressure coordinate system. That is extremely complicated. If you want to try it, I encourage you. I tried it several times, it's really, really, really complicated because there are so many terms that appear. It's much easier, and that's what we are doing here, to go back to first principles, to go back to the defining law for the continuity equation, which is we consider the conservation of mass for an infinitesimal element. So we write down the mass element definition, which is equal to the density times the volume, variation of our volume element, which can be written, if we go back to Cartesian coordinates for simplicity here, dx times dy times dz, which can be, and now comes our property of the hydrostatic equation, we can replace the variation, any variation in dz, in z, using the hydrostatic equation, which we are doing here. Then a minus sign comes into play. Now, if we are looking at the time derivative of a relative variation of our mass element, that time derivative should be, following the motion, should be 0, because following motion, our mass, our infinitesimal mass, should remain constant. That's the conservation of mass, following the motion. If we write this down using the definition of this mass element here, but this is just a reformulation, but that is equal to 0. Now we have to apply the total derivative to each of these terms using the product rule of differentiation, yes. And we get to this equation here. We can reverse the order of derivatives here and come to the conclusion that this means that the variation of u with the variation of x plus variation of v divided by the variation of y plus a variation of omega divided by a variation of pressure, this has to be 0 in this case. And then we can let again our mass element become infinitesimal, and then these deltas become differential operators. So our continuity equation in the pressure coordinate system degenerates from a fully prognostic equation that we have, exactly speaking, in the three-dimensional z coordinate system. We get a diagnostic equation. There's no time derivative anymore. This looks almost like our incompressible fluid, only that this is now exact for considering the hydrostatic equation exact. So it's a very, very, very precise law, only that we have posted in this pressure coordinate system. So it seems actually we are losing not only one prognostic equation, which is the vertical equation of motion, but we lose another prognostic equation, which is the equation for the density, the continuity equation. But it turns out, actually, if you want to write a model with these equations, you will need in the end an equation for the surface pressure, a prognostic equation for the surface pressure, which is additional. So it's not quite true that we really lose two prognostic equations. The thermodynamic equation. Remember the thermodynamic equation from thermodynamics? What does this equation tell us? This is the equation for, does someone know? What is this quantity Vp times dt, change of temperature? What is this? Does someone know the change of enthalpy? Have you heard about this? the first law of thermodynamics expressed in terms of enthalpy. We can express the first law of thermodynamics in many ways. But one way is to express it in terms of enthalpy, in which case on the second term here has to have the derivative of the pressure. Otherwise, there would be the derivative of the specific volume if we take into account the internal energy, not the enthalpy. Remember that from your thermodynamic course, these Legendre transformations of the energies. So this is just the rate of change of enthalpy for our parcel. And as you can see already, so temperature is not a conserved quantity. But you could integrate this. You could integrate this indeed using the perfect Gauss law that has been already inserted here and show that potential temperature is a conserved quantity following the motion, because you eliminate this term here. You can almost do this in your head. If you divide this by temperature, you get d by dt ln, something like ln logarithm of temperature. And here's the d by dt of logarithm of pressure. So you can combine them, and that gives you the definition of potential temperature. But that can be equaled, for example, when I did some years ago the thermodynamic course, you can show, of course, that if we have the only diabatic process we consider is the condensation, giving a rising parcel, we can have condensation. Then the only term on the right-hand side that can appear here is this transformation term from or the heat gained by condensating parcel, for example. Remember this term from your atmospheric physics course? So what is this L standing for? Can someone answer? Can someone make a guess? Is the latent heat of condensation. And M would be the mass ratio of the mass fraction of water vapor, which is equivalent to the specific humidity Q. So this would be one way to express a diabatic heating term on the right-hand side. But in reality, there can be many more. This would be just the term where we consider a rising parcel, a moist rising parcel. Now, otherwise, if the air is not moist, then the right-hand side here would be 0, and our potential temperature would be constant. But if we have the possibility that in a rising parcel, the water vapor is condensing, then we may get this additional term. But in reality, there may be many other diabatic processes that change the temperature. One very important one could be radiation. You may want to include the possibility that radiation changes your temperature. Or frictional dissipation. Frictional dissipation will also change your temperature. Many boundary layer processes will change your temperature. So we are kind of very lazy and say everything that contains these diabatic terms are just abbreviated as Q on the right-hand side here. All the terms, including the diabatic heating term, all these terms are abbreviated as Q. And most of the time, if we want to understand something practically, it's very useful to set Q to 0, because that is very powerful. That is the adiabatic reversible version, in which case potential temperature is conserved following the motion. But in general, let's say we leave Q here for the time being. Now, so when we can write this exactly in the pressure coordinate system, splitting in the, we note already, one thing we note already, the reason why we have written down this temperature equation, or the equation, the first law of thermodynamics in enthalpy notation, is because we have the dp by dt here, which is just the vertical velocity in the new coordinate system. And then also the total derivative contains another term that is proportional to the vertical velocity. Omega times dt by dp is the vertical derivative here. So we can combine these two terms and just leave the horizontal advection terms. So our thermodynamic equation and pressure coordinate then takes the convenient form local time derivative plus horizontal derivatives, keeping always, in this case, the pressure constant, minus a factor, which we will analyze now here, a stability factor, times omega is equal to Q over Cp. So we have divided by Cp. In this stability factor, and you will show this in an exercise, contains a term that is just taken from this, plus a term that is taken from the vertical derivative here. That can be expressed as T over theta d theta by dp. We have used the definition of potential temperature. Now it's written here. You all know this definition already from your thermodynamic course. This nonlinear transformation of between temperature and potential temperature. But if you use this, you can show that the stability parameter can be expressed as the lapse rate, the dry adiabatic lapse rate, the one that you named, which is about 10 Kelvin or 10 Celsius per kilometer, minus the actual lapse rate of the atmosphere divided by rho over g. So if the atmosphere is stable in the large scale, which we always assume, then this stability factor, SP, is always positive. Only if our actual lapse rate becomes like the dry adiabatic one, then this can become zero or even negative if this is larger. But for our large scale, at least theoretical considerations, this will never be the case. Our stability factor will always be positive for large scale considerations. But this is not a strict need. So if you use this equation, for example, in a numerical model, this stability parameter could also become negative. It doesn't mean that the equations are not valid anymore. It could become negative and then it's negative. But for most of our practical use, we will make use of the fact that this stability parameter is always positive in the free atmosphere. And we will make use a lot of this equation, in particular some key approximations to this equation in the future of this course. So this is a very important equation. Now, this set of equation, the thermodynamic equation, together with a continuity equation, which is the divergence-free equation in pressure coordinates, the hydrostatic equation, and the horizontal momentum equation, they build up a set of equations that is essentially used in many, many numerical models of the atmospheric circulation and in climate models in general. This is the set of equations that is often used. We can also transform the potential vorticity now, just for consistency, let's say, into the pressure coordinate system remember that the potential vorticity was proportional to the vertical gradient of the potential temperature, which then can be expressed using the hydrostatic equation as this. And then something useful happens, because the density out of the potential vorticity, the density drops out. Just like in the pressure gradient force, where the density drops out. So the potential temperature in the pressure coordinate system becomes just a product of two terms. It's just a curiosity. Okay. It is almost 11 now. Do we want to have a short break, or do you prefer to continue? 10 minutes break is okay? Yes? Okay, let's have a short break. Yes, okay. So we are back. Let's say we want to understand some properties of the extratropical flow, for which this quasi-geostrophic approximation is so important. Let's have a look at this figure here, which kind of we have already looked at in the model framework, but now we want to look at in this different framework. So what we see here is from the South Pole to the North Pole, zonally averaged fields. So all the fields that we are looking at, they are averaged out in the x direction, total average in the zonal direction. So we can only display from the South Pole to the North Pole, and from the surface to, in this case, 100 hectopascal. But if you look at the numbers here, yeah, I said already hectopascal. So the coordinate system we are looking at here is the pressure coordinate system. So, for example, at the surface, we have about 1000 hectopascal, and then we go up in the atmosphere, the upper atmosphere. So we are making already use of this fact that we can look at our fields equivalently in this pressure coordinate system as compared to the Z coordinate system. So Z goes up in this direction and pressure goes up in this direction. Now, the field we are looking here is now the temperature, but it's not just the temperature, but it's the temperature minus a reference temperature profile, which is a mean profile only depending on the vertical direction. So we kind of remove the vertical profile of temperature by subtracting a zonal and a meridional and temporal average temperature. And this is for boreal winter, so DJF, and it's a long-term mean situation. So let's say 50, 60-year mean from the 1950s to 2020 or whatever. And then in terms of temperature, of course, you see that it's relatively warm on average on the equator and cold in the extratropics. Well, also in the southern hemisphere, but less the case because we are in southern hemisphere summer and in northern hemisphere winter. But what is highlighted in this curve is this strong temperature gradient between the tropical regions and the extratropical regions. Emphasized by instead of looking at the temperature, looking at this temperature anomaly, let's say. And then if we look at the wind, we again see something that we already used to look at. So we see this positive, this is now the U wind component. Same display, so again, South Pole to North Pole, surface to 100 hectopascal, which is about 100 hectopascal is already stratosphere everywhere. 200 hectopascal is about more than 10 kilometers already. So that could be the limit between stratosphere and troposphere in some regions. And we see this positive U jet. So there's this jet, which is on top where this temperature gradient reverses. You see it reverses in the stratosphere at some point. Then this jet is maximum and it also becomes weaker if we go up. So this is again this interesting relationship between the temperature gradient and the change of wind with height that we can derive here. This is a very, very useful equation that, again, if you stay in meteorology or climate, you will use many times. This is called thermal wind equation. It's very useful. And you will derive this in an exercise from the momentum equation and from the hydrostatic equation. You will derive that there has to be, if we are in geostrophic and hydrostatic balance, there has to be this relationship between the meridional temperature change and the change of the winds with height. This is just for one component, which is relevant for the fields that we are looking at here. So whenever we have a meridional temperature change or gradient, we have to have that our winds are changing with height in such a way that in our case, when this temperature gradient is negative, then the wind has to decrease with pressure or to increase with height, which is exactly what we have seen in the jet streams in these mid-latitudes that we have seen. And you can, of course, you can derive a similar equation for the meridional component of the wind, which is then related to the zonal temperature gradient. Only that for our case here, this equation is more relevant because we have averaged out all the zonal differences. So this is a very, very powerful equation, diagnostic equation that is always valid. And as for all diagnostic equations, you can never say what is the cause, what is the effect. Sometimes a temperature gradient can be the cause for the vertical wind shear, but sometimes the vertical wind shear can be the cause for a temperature gradient. They have to be in a very good balance always. Most of the time we may find that it's likely that the meridional temperature gradient is responsible for the vertical wind shear. Definitely in our case here, where we have this strong temperature gradient that can be interpreted as induced by the differential solar radiation on average, and particularly here in the northern winter, that leads to a strong temperature gradient, and then that leads to this polar subtropical and polar jet strong winds that everybody knows well who's flying in the North Atlantic, for example, or in the Pacific. They know this the presence of this jet stream very well. Now, of course, we find a similar situation for JJA, for the boreal summer, only that then the temperature gradient and correspondingly the jet becomes weak because the heating is shifting to the northern hemisphere, and so also at the pole there's a lot of solar radiation in the summer hemisphere, and so that temperature gradient becomes rather weak, whereas in the southern hemisphere then we get the stronger jets. So that is completely consistent. However, if we look now at a picture of this jet, not anymore zonally symmetric, but we just look at a one pressure level, which is here the 200 hectopascal level. So the level where this jet seemed to be maximized. If we look at this level, we see that this jet is not just a zonally symmetric feature, but is localized. And it's localized where we have the strongest temperature gradients. So it's localized at the east coast of the continents. In the Pacific, the jet is a little bit more zonal, but in the Atlantic, this jet is pretty much tilted. So there are interesting features in this jet. So in reality, the mean situation actually should vary also in the zonal direction. This is just now a time mean picture. And you also see this feature here, these negative winds at upper levels in equatorial regions. And this feature is called a tropical easterly jet. So probably some of you who have studied tropical meteorology have heard about this feature. It's not everywhere, but in the mean, even in the mean, we see there's this feature of the tropical easterly jet. Of course, there are the trade winds that are well known. Then we have the westerly winds, and then also we have this tropical easterly jet feature in the mean, weakish. Okay. So what is happening then in these mid-latitude regions is that perturbations, as we have already seen in the first lecture, they may grow from time to time because of the strong temperature gradient that leads to this baroclinic instability, that within a few days, waves or perturbations in the flow, which are raspy waves, they can grow or they can decay depending on the situation. That is the baroclinic instability feature. Now, before discussing the details of these raspy waves, we want to revisit this geostrophic or quasi-geostrophic approximation. We have used this already in principle, but this is now a little bit more systematic way to do it, and we do it based on this system of equations derived for the isobaric coordinates, for our pressure gradient, for the pressure coordinate system. So we are using our set of equations that we have just derived to make this analysis, to derive a simpler set of equations that can be used to understand some features of the general circulation already. So the velocity can be always, this is the horizontal velocity, can be always expressed as its geostrophic component plus an additional component, which has to be, by definition, the ageostrophic component. And we know already, and we will see this later, that the geostrophic component of the wind is much larger, the magnitude, than compared to the ageostrophic component, if we are concentrating on our large-scale features. The geostrophic wind is defined in this way. So in order to define the geostrophic wind, usually we use a constant Coriolis parameter. There's a reason for this. This Coriolis parameter could be valid at some base point in the extratropics, let's say at 45 north, if we are interested in flow variations about in that region. With this definition, and that's the reason why we use a constant Coriolis parameter. With this definition, the geostrophic wind is non-divergent because it's defined exactly by a stream function. Otherwise, if we use a Coriolis parameter that can change with latitude, then this geostrophic wind would have a divergent part too. So in order to distinguish the divergent and non-divergent winds as kind of geostrophic and ageostrophic winds, it is more convenient to define the geostrophic wind in this way with a constant Coriolis parameter. Then, as I just said, we note that the ratio of magnitudes of ageostrophic and geostrophic wind scales just as the Rossby number, which we know should scale as 10 to the minus 1. So the ageostrophic wind should be 1 order of magnitude smaller compared to the geostrophic wind. We have made use of this property already in principle by identifying that the divergence is also 1 order of magnitude smaller than the vorticity, which is approximately the geostrophic vorticity. Now, in the momentum equation, it turns out a quite convenient and useful and accurate approximation is to approximate the velocities and the terms in the present in the total derivative as the geostrophic parts. So this geostrophic, the change following the geostrophic motion would just be determined by the UG d by dx and VG d by dy term. Then a further thing that can be done is useful to do is to derive a Taylor series expansion for the Coriolis parameter. So we have already made use of this constant term f naught, which is kind of mean value in mid-latitudes, plus a variation of the Coriolis parameter around that latitude. But also here, we have to assume in this quasi-geostrophic approximation that we do by making the use of this mid-latitude, what we call beta plane, that the F naught is always much larger than beta times y. That means we cannot go too far away from our base point. We can only go away maybe 1,000 kilometers or a few thousand kilometers, but we cannot go all the way to the equator or to the pole. So we have to stay in some kind of channel in the mid-latitudes so that our approximations are valid. So again, this beta times length scale divided by F naught should be the order of the Rossby number, so much smaller than 1, 10 to the minus 1. So we cannot go too far away from our base point. We definitely have to be, our length scales have to be much smaller than the radius of the Earth, for example. But that can be easily kind of constrained in our consideration. Then we may, if we want to understand the accelerations of our geostrophic wind, which are governed by the right-hand side of the momentum equation, which is, well, it's not written here anyway. So this is these are the terms governing the acceleration of our geostrophic wind. We can insert these decompositions of the geostrophic wind and ageostrophic wind, and of the beta parameter and the constant coronas parameter plus the beta deviation term. And of course, insert also here again the definition of the geostrophic wind. Then the largest terms here, they cancel out. And as first order terms, we have the balance between F naught and the ageostrophic wind here, plus a beta term multiplied by the geostrophic wind. And then there's a second order term here that is small, 1 order of magnitude smaller compared to the other terms. So the main term for the acceleration of our geostrophic wind is determined by the competition of these two terms. And the interpretation will become very intuitive later on. Okay, so with this, our approximation of the horizontal momentum equation looks like this. Instead, the continuity equation in pressure coordinates looks like this, because the horizontal divergence of the geostrophic wind is 0. So the divergence of the total wind is just the divergence of the ageostrophic wind. So it's the ageostrophic wind, in principle, using this diagnostic equation that is responsible for vertical motions, if you want. The geostrophic wind itself doesn't cause any vertical motions. For the thermodynamic equation, it's very useful to do something that we have seen in the pictures already that we have just looked at. It's very useful to decompose the temperature, the total temperature, in just a vertical reference profile, which could be the mean, time mean, zonal and horizontal and time mean temperature, which is just vertically dependent, plus a perturbation from that. And then we assume that most of the variations in the vertical direction are actually contained in this reference temperature part, which is indicated in this equation here. Then we can express our temperature equation in this way. It's the local temperature change plus the geostrophic advection of temperature. And we get this vertical part here, proportional to the vertical velocity, which includes this kind of newly defined stability parameter, which in this case only depends on the reference temperature profile. So it's just a more convenient way to look at the equations. Now the quasi-geostrophic vorticity equation. Our quasi-geostrophic vorticity, okay, our geostrophic vorticity is defined as the vorticity, the vertical component of the vorticity, just using as velocities the geostrophic velocities. And then we come to the conclusion that it's of course defined as 1 over F naught times the Laplacian of our geopotential. But, and this will begin again in exercise, you see the most interesting things are done in exercises. So you can use, just as you used already the momentum equations, you can use this new momentum equation, apply the definition of the vorticity and derive this new vorticity equation. And you see the result that we get is exactly the same form as the one that we have derived using scale analysis of a more complex vorticity equation. Now here we have done kind of an approximation before, have an approximated momentum equation, and then you can derive exactly this vorticity equation. Before we have done the opposite, we have derived a more complete vorticity equation, did a scale analysis and found that the terms that you see actually here are the most important terms. So the change of vorticity following the geostrophic wind of the geostrophic vorticity is given by the divergence term and the advection of planetary vorticity. And then you may slightly reformulate this using the continuity equation, and you may split also from the total time derivative of the relative vorticity. You may split just the local time derivative. And then it turns out that if we don't have orography or strong diabatic heating, then often this term here on the right-hand side, this divergence term, can be occasionally small. And in fact, for the derivation of Rossby waves, of the dispersion relationship for Rossby waves in the next section, we will assume that this term for that consideration is 0. Because there's an interesting cancellation going on between these two terms. So we are now looking at what is happening between these two terms in principle that govern this local change of relative vorticity. And these two terms are the advection of relative vorticity and the advection of planetary vorticity. Now assume we have a wave. Nice wave, okay. And assume we are in this position here. The flow direction is, the mean flow direction is this. So the air parcels are moving in this direction. And this wave could be, the wave that we see here could be in geopotential. So this could be a line of constant geopotential at 500 hectopascal, let's say, at some mid-atmospheric levels. And then our air parcels move around here. We have already understood why our air parcels move around here, because if we are here, let's say we are in this position here, we move to the north, then our flow has to become, because of vorticity, absolute vorticity conservation, have to become anticyclonic. So we turn anticyclonic, then we move to the south. Then, because then our planetary vorticity becomes smaller, so our relative vorticity has to become larger, cyclonic, and we move to the north again. So that can be explained. But we want to understand, for example, let's say we are in this position here. What will be the change of the relative vorticity? One effect is the advection now. So since there is a mean westerly flow, the vorticity will be advected, the positive vorticity would be advected in this direction here. So we expect in this position here, where the vorticity is probably 0 in this case, we would expect that the advection of relative vorticity makes the vorticity here positive. But on the other hand, we have this other term here. Since we have southerly flow in this case here, northerly flow, so this is positive. So the advection of planetary vorticity is negative. So that would reduce the tendency of vorticity here. So there's a general tendency for these two advection terms, the advection of relative and the advection of planetary vorticity, to cancel each other. And when they exactly do this, when they do exactly cancel each other, then we have the stationary case. Then the Rossby wave is stationary, doesn't propagate, because there's no tendency for vorticity anywhere in that case. If these two terms exactly cancel each other, and this term is zero, because we said we consider cases now where we assume it is zero, waves do not grow or do decay, then stationary waves are characterized by the compensation of these two advection terms. And this is exactly the case that we may make use of by tomorrow when we, in our lecture about Rossby waves, we will derive the dispersion relationship for Rossby waves, and we will derive the special case of stationary Rossby waves. In that case, will be exactly determined by the compensation of these two advection terms. But it also turns out that if we have, so the stationary Rossby wave is governed by one specific wavelength. So there's one specific wavelength that makes Rossby waves stationary, given a mean flow and given the Coriolis parameter and so on. But the structure of these terms tells us that this first term here contains many derivatives. There is a relative vorticity here, which is already a Laplacian of this field here. And then there is a derivative of this. So that tells us that short waves that are characterized by a high kind of high wave number, then the fact that we have the Laplacian of the geopotential appearing here makes that this term will be very large when we have short waves. So short waves will be just dominated by advection, and the planetary advection term may not be important. So the rule is that short waves would be just flow with the mean flow, short waves. Whereas very long waves, then this term becomes small, because the Laplacian of the geopotential becomes small for very long waves. Then the second term becomes dominant. And so long waves, very long waves, they tend to move in the opposite direction. In the westerly direction. And so it's the stationary waves that has this special property where the two things just compensate each other. Yes, I think this is more or less what I wanted to talk about today. Again, there are some exercises. They're accumulating now. I encourage you then, if of course by tomorrow, I don't think we have a lot of time, because during this week we have kind of a accumulation of lectures. But I encourage you over the weekend to definitely to go through these exercises. And if there's any problems, better ask. Then we can discuss the outcomes of this. Okay? So see you tomorrow. Bye.
Bye. Bye. Thank you.
Thank you.